Hi, as promised in the previous video, this video is going to be about how to read a textbook and what we expect from students when we say, go read the textbook and look at this topic. I wanted to reiterate something I said in the previous video, which is there are going to be cases in our classes where we say we expect you to learn this on your own. And again, that might be a shift from high school where, at least in my high school experience, pretty much everything that was going to be on the test was talked about in class. That isn't the case in college. There are going to be things that you will be expected to know for exams that we don't cover in our lectures at all. They might be in notes, or there might be something in the notes that say, go read and understand material related to significant figures on your own. And there will be some homework problems about those things. You're always welcome to ask us questions about those things. But again, just because we don't lecture on it doesn't mean that it's not going to be on the exam. In fact, that's just the opposite. There are definitely things that show up on exams that are topics that we don't discuss during the lecture period. So with that said, we're going to focus on these pages, again, in my book, 36 to 38, but the section on uncertainty, accuracy and precision. And I've read through this and trying to think about, the student view of things. So I'm just going to point out a few issues or things that I would hope that students get out of having read this section. Okay. Notice each one starts with the aim. Each section will start with the aim. So this is really, in some ways, telegraphing. The author is telegraphing to you what you should get out of this particular section. So this is something to pay attention to. We want to be able to define accuracy and precision and ultimately apply proper rules to rounding. Now, I would ask you to pause the video and perhaps reread just this paragraph and say, what do I take away from that paragraph? Okay, and for me, the takeaway would be that when we actually count something rather than measure it, then we know it exactly. If I've got 56 lima beans, then I know that there are 56. I can count them. Somebody else could count them, and we'd end up with 56, and we would know that number exactly. So 12 in a dozen is an exact number. Notice here they also talk about exact conversions. 1 inch is exactly 2.54 centimeters. There is no what we'll eventually call uncertainty in that. Okay, so that section lays out what an exact number is. Now, again, a difference between high school and college is, I think in high school, we would say, oh, that word is in bold, so I'm going to highlight it and I'm going to memorize the definition. Well, notice they don't give you a definition of an exact number. They're telling you about what exact numbers are. So you have to come up with that definition. So there is no an exact number is a number that is something that is counted by measurement and can be known without any uncertainty. There is nothing to memorize there. It's a concept to be understood. So on my exams, and I think this is true of my colleagues, you will not find the question like define an exact number. What we will do instead is ask a question, which of the following is an exact number? The number of lima beans in a package, the volume measured in a graduated cylinder, those kinds of things. So it's not only knowing the definition, but it's being able to apply it. Right? And that might be a change or a shift in how you think about the material. The next thing that I would hope students note in this is this particular picture. There is the old adage that says a picture is worth 1,000 words, and that is incredibly true of textbook pictures. The pictures reinforce the text and, in fact, are oftentimes easier to understand in terms of what's going on than the text. Again, as a textbook author, I can tell you most of my time went into creating figures that I thought really illustrated the principles that I was trying to get across. So a lot of chemistry is a physical science. It's about the world. So we can represent things about the world really well using pictures. So that's what a lot of textbook authors will use to do that. So here we've got a picture of a graduated cylinder, and notice what they're doing. They've got the box, and the box is saying we're going to blow up that box. We're going to focus just on that area. And then if we really zoom in on that area, notice that we've got this liquid line here somewhere between 20. And if we go back to this, we'll note that this is 20 to 25. So what does each one of these lines represent? The author's not telling you that. So each one of these lines represents one. Right? So this line is 21. We're expected to be able to figure that out for ourselves. So this line here will be 21. This line here will be 22. Notice right now, I'm doing work on my book. I'm not just staring at a picture. Okay. I am actively looking at this, trying to understand it, trying to figure out what's not being told to me about it. And then if you read the text below, they're trying to say, hey, this is an estimate. If I want to get the volume, I know it's somewhere between, this is 20, this is 21, and that's 22. So I know the volume is between 21 and 22. I know for sure that it is above 21, and I know for sure that it is below 22. So those two numbers, I know really well. The next number, the decimal place, I'm going to guess at. And they suggest that a guess is 21.6. Now, somebody sitting next to me could say, I don't know, I'm going to say it's 21.5. Somebody else could say, well, I don't know, I read it as 21.7. Notice there is some uncertainty in that number. That's all uncertainty is about, is where do we begin to lose confidence? We were confident that it was more than 21 and less than 22, but now we're not so sure if it's 6 or 5 or 7. And we certainly wouldn't say 21.69387, right? We don't have the ability to measure it that well based on what was presented. And we deal with this all the time. If somebody were to ask you, like if somebody were to, I'll make it personal. If somebody were to ask me, what do I weigh? Okay. Well, before COVID, I would have said 180 pounds. Now I have to say about 185, and if I'm honest, 186 pounds. But notice I don't say I weigh 186.97321 pounds. And in fact, I'm rounding it to 186. I don't even say I weigh 186.2. Well, why not? Because my scale doesn't measure down to the tenths of a pound, right? So what we're saying in uncertainty is really just how well we can make the measurement. It is conveying to the audience what we think we know well and where the first digit of uncertainty resides. Okay, so that's what this figure is about. Notice how long we spent on that figure. Okay. Take a lot of time to understand figures in the book. They really help. The next thing that I wanted to discuss, you see that I've underlined a few things here. Again, I'm not a big advocate of tons and tons of underlining and highlighting. I think you have to be strategic. Otherwise, you just think everything's important, then it's impossible to go back and study from. But whenever an author uses a word like pointless, that gets my attention, right? Note that it would be pointless to attempt to estimate a digit for the hundredths point, given that the 10th place is uncertain. Okay. So that's the point that I was just making, that unless we have a way to make a measurement that to that level of certainty, we stop at the first digit where we're guessing. And in that last problem, it was the 0.5 or 0.6 or 0.7. Okay. So here then we transition. So again, I'm expecting that you have read this. I might even stop and I suggest pause the video at this point and reread this paragraph. Okay, hopefully you're back on. And notice now they re-emphasize some of those ideas that we saw with the milliliters. Now they're doing it with a quarter on a balance, 6.72 grams, but it could, even when it's a balance, and the balance is telling us 6.72 grams, the last digit of any measurement system, like a balance or a spectrometer, a gasoline pump, right? Do you believe the gasoline pump gallons down to the last digit that they show you? You probably shouldn't, okay? So a balance, the very last digit that it shows you, is not certain. That's where the balance itself is guessing. So here they're talking about a balance that's guessing between 6.72, 6.71, 6.73. And when you're actually in lab and you put something on the balance, you're going to notice that last digit fluctuating. And you're going to get in the habit of sitting there staring at it going, wow, I wish it would stop fluctuating. And that's just the inherent nature of the balance. So don't wait for it to stop, because it's really just kind of saying, hey, I don't know that digit. And that's what it's speaking to you as you're waiting. So just understand that that last digit is uncertain. Okay. And then here again, we say every measurement has some uncertainty. And notice they're not defining the uncertainty even though it's bold. They're asking you to figure out what it means for something to be uncertain. And the uncertainty is just how well you can report that measurement. Okay. And now they're going to introduce all of the digits in the measurement, including the uncertain last digit, are called significant figures. So these would all be significant figures. These would be called significant figures or significant digits. Then they have this important thing that says, note that 0 may be a measured value. For example, if you stand on a scale that shows weight to the nearest pound and it shows 120, then the 1, the 2, and the 0 are all significant values. But they're also going to allow themselves the possibility that it might not be a significant figure. Okay. So clever reading of a textbook is required. They're not saying 0 is always a significant digit. Whenever you make a measurement properly, all of the digits in the result are significant. Now, this confused me. I have to be honest, I had to go back and reread this 3 times when I was first reading this because it didn't make any sense to me. And all they're really saying is whenever you make a measurement properly, all the digits are significant, meaning properly is you didn't goof, right? So you didn't have some kind of inherent error, like with the balance, you weren't pressing on the balance at the same time. Like if I want my weight, that it was zeroed properly, that I started at 0 and my kid brother wasn't stepping on the scale at the same time to make it look like I was heavier. So that's all they mean here by properly, is that we did it right. Right? But then they say whenever we make a measurement, all of the numbers are significant. So in this case, that 6.72 is a measurement. All 3 are significant. Okay. But what if you were analyzing a reported value, meaning somebody walked up to you on the street and said, here's a number? That's what they mean by a reported value. Now, you might not have caught that the first time. Ask yourself, did you? Did you understand what they meant by a reported value? Okay. And if not, you're just learning that in the textbook, there's some of these words that are kind of coded or need to be analyzed and understood. Okay. Speaking of that, I want to go back to a word. Meniscus. Maybe you haven't heard the word meniscus before. Do you know what a meniscus is? If you didn't, did you stop? Did you look it up? Did you Google it? Or did you just keep right on going? Because they use meniscus, again, several other times, right? Somewhere else here, I can't, here, the meniscus, the appears. So if you didn't know the word, then reading probably didn't have a whole lot of meaning to you. Now notice they do offer a little definition, the lowest point on the curved surface of the liquid. So by the meniscus, what we're really talking about is that curve, and we'd be reading at that lowest point. Okay. So if you found yourself in the habit of not stopping to figure those kinds of things out, that's going to be something to pay attention to when you start college classes or this summer as you're preparing to transition into college. Now, let's deal with these pesky zeros. We will use the terms leading, trailing, captive for zeros, and we will consider how to deal with them. So again, this is a really important figure because this is where they're defining what they mean by those 3 terms. I should point out too, notice if I go back to meniscus, sorry, I hope I'm not making you seasick, but if we go back to meniscus, that wasn't bolded. And here they do offer a definition for it. So we just have to be smart readers of the textbook, right? And use it rather than just try to consume, just words. So if we look at that, trailing zeros are the zeros that come at the end of a number on the far right side of a number. Captive zeros are ones that are captive between 2 other numbers. And leading zeros are exactly that. They lead, they come first, so they're on the far left. Now, here's a sentence that I think I needed for sure to reread multiple times. Starting with the first non-zero digit on the left, count this digit and all remaining digits to the right. This is the number of significant figures in the measurement unless the last digit is a trailing zero lying to the left of the decimal point. If I got up to you in front of the class and I said to you, we're going to learn about significant figures. Starting with the first non-zero digit on the left, count this digit and all remaining digits to the right. This is the number of significant figures in the measurement unless the last digit is a trailing zero lying to the left of the decimal point. Would you understand that? Did you understand it when you read it the first time? I didn't. I had to go back and I had to take it apart. So, okay, starting with the first non-zero digit. What does that mean? Something that isn't zero. So did you key into that non-zero word? Because this is the rule. This is telling us how we're going to count significant figures, which is an important thing. Okay. So if we look at something like 6.72, well, the first non-zero, 6.72, the first non-zero digit is 6. So that's the first digit on the left. And we're going to count that digit and all remaining digits to the right. Well, that's 1 digit, that's 2 digits, and that's 3 digits. 6 and 7 and 2 are all significant here. So all 3 of those are significant. So we'd have 3 significant figures in this number. This is the number of significant figures in the measurement, unless the last digit is a trailing zero lying to the left of the decimal point. You might say, well, what about this? Is that significant or not? I'm going to ask you to pause the video and determine if this is significant or not. If you don't already know, reread that sentence. Okay. Notice, where does this zero lie relative to the decimal point? It lies to the right of the decimal point. Okay. So this rule, unless the last digit is a trailing zero lying to the left of the decimal point, doesn't apply to that zero. Does it apply to this zero? Well, if we put a decimal point right there, which 3090 you could think of as having a decimal point there, well, now we have a trailing zero. It's not between two numbers. And it does, in fact, lie to the left of the decimal place. So, coming back to our sentence, this is the number of significant figures. So we said something like 6.72 would have 3 significant figures, unless the last digit is a trailing zero lying to the left of the decimal point. Okay, so we might be tempted to say this is 1, 2, 3, 4 significant figures if we didn't have the decimal place there and we were just counting from left to right. But now we have this rule, unless that zero is a trailing zero to the left of the decimal point. So this zero counts as that exception. So this does not get counted as a significant figure. So how many sig figs do we have then? We'd have 3, not 4. All of that is packed into that sentence. Okay. And it requires effort to unpack all of that. Okay. So then notice what the textbook authors do. They go on and they illustrate exactly what they just said. First non-zero figure on the left, and then they say 1, 2, 3, 4. So this has 4 significant figures. 55.0, first non-zero figure on the left. And then we count over and we get 3. But notice, are we going to count this 0 or not? And if so, why or why not? Where is it relative to the decimal place? It's here. No, notice if we go back to this meniscus picture, what we're really saying here is, imagine we had a picture where this was 21 and this was 22. And I draw my meniscus and I do that and I ask you to read this. Well, you know for sure that it's 21, and you know for sure that it's not like 21.2, right? Here you might guess 21.2. So if this was 21.2, you're really allowed to say, no, that's right on 21. So I'm going to guess that last decimal place is 21.0. It may be, oops, sorry about that. I hit the camera. It maybe dips under a little bit. So yeah, maybe it's 20.9, maybe, but I think it's 20.0. Might even be 21.1 if it were just a little bit higher. But we're guessing at that, but I'm allowed to guess that 0. And again, we'd get 3 sig figs. Okay. And then we have the last examples here. First one has 5 significant figures. All of these, the zeros are both captive or embedded between numbers. And then lastly, we have this example. And notice this asks us to go back to starting with the first non-zero digit. Okay, so you might, if this were a problem in the back of the book and it asks you how many sig figs, you might originally say 1, 2, 3, 4, 5, 6, 7, 8, 9, and you might answer 9. And then you look at the answer in the answer key and you go, oh, no, it says 6. Why is that? What I'd ask you to do as students is not just say, oh, okay, that number has 6. And it tells me it's 6. The author doesn't care, really, about the number 0.00832407 and how many sig figs are in it. The author cares about the general principle that you know how to count significant figures, because the significant figures tells the audience how well you've measured something. Right? If I know the distance between here and the moon to 19 significant figures, that's a lot more impressive than knowing the distance between here to the moon and 2 significant figures. It's a much more accurate measurement. Okay, so in this case, we come back to that non-zero digit rule. We're not going to count the leading non-zero digits. We start with the first non-zero digit. 1, 2, 3, 4. We come across another 0, but it's captive. So we count that. 1, 2, 3, 4, 5, 6. Okay, so this would have 6 significant figures. And they offer an explanation for why. And their explanation for why is because we could really represent this number as 8.32407 times 10 to the minus 3. And now if we counted significant figures, we only count the significant figures in the actual number. We don't count the 10 to the minus 3. Those act like placeholders. That's telling us is the first significant figure in the tenths or the hundredths or the thousandth place. And that is not a significantly measured number. It just tells us something about the magnitude of the number overall. Okay. So look at how long we're spending working on this. And I've been doing this for 22 years now, teaching college, and it still takes me that long to go through this material and digest it and try to re-explain it to you. But your task is going to be to digest it for yourself and re-explain it to yourself. Right? And then, of course, they have the very last section here where we have this example. How many sig figs are in there? Well, it tells us these zeros could or could not be significant. When there's no decimal place, it's ambiguous. So rigorously, most people would say this has 2 sig figs because these would be to the left of a decimal place if a decimal place existed. If we stick a decimal place in there, we are acknowledging to the audience that we know that it is 1300 decimal place and that those 2 zeros now become significant. It's a small little rule. Don't get wigged out by that. If there was a decimal place there, most people would now say that there are 4 sig figs, that putting the decimal place removes the ambiguity, that the author has chosen to put that decimal place to say that they know it is exactly 1300 or 1301 or 1299. That last digit is still uncertain, but it's still a significant figure. And then notice they go on to say, look, the US Census said that there were 317,297,725 people. And they ask you, realistically, do you believe that number to be true to 9 sig figs? And hopefully you say no, because there's no way we can possibly know at any given moment in time how many people are alive in the United States. So that's that section. Now, here's the key thing. Having read that section, we would want to test ourselves before we go on to the next section. So to test ourselves, we go to the back where there are problems. So some of this is knowing how to use a textbook again. And we look for problems that are going to test the skill we just learned. And that would mean, going through here, I just happened to turn to this page, this visit the Fet Density Simulation. These Fet simulations are fantastic. And in the PDF of the textbook that I showed you in the previous video, there are direct links. There's no reason not to click on those things and use them. There's a little, Fet used to use Java, and as the world moved away from Java, Fet has had to change to using a different platform, so hopefully they still work. But if these work on your computer, use them, and don't just play with the videos, study the videos. Try to get principles out of them. But this has to do with mass and volume and density. There's some other problems, 44 through 47, that deal with accuracy and precision. But somewhere there's going to be problems that deal with significant figures. Right? So then it asks you to calculate the number of significant figures. So real quick, how many sig figs do you see? Good, 2. How many sig figs do you see? You should say 3. The 2, the 0, and the 5 are all significant, because the 0 is captive. How about 86,002? Well, these 2 zeros are significant because they're captive between the 6 and the 2. So this has 5. What about the 9.740? And do that one, and do that one, and do that one. Let's say I said 3 for F. 1, 2, 3, 4, 5, 6 for that one. I'd say 4 for that one, 1, 2, 3, and I'm going to say 3 for that one. Okay. Now, how do I know if I'm right? Well, in the back of the book, there's answer keys. So I find the chapter. So here's chapter 1. And we were doing problem, turned out to be 49 in my book. And again, there might be some variations in the PDFs, but you will find, I guarantee, problems about sig figs. And notice 49 has the answers. There's 2, 3, 5, 4, 6, 2, and 5. So I've got all of them right except for the last 2, 2 and 5. So they're telling me the right answer is 2 and 5. Well, I wrote down 3 and 3. What did I do wrong? I don't want to be content by just saying, oh, well, that's a 2. 0.017, anytime I see 0.017, I'm just going to say 2 from now on. Because if I give you a test and I say 0.349, how many is that now? You might still say 4 because you're in the bad habit of counting everything. The principle here is that the 0, the leading 0 here, does not get counted. We talked about we start counting from the first non-zero digit. So we'd want to go back and refresh our memory of that rule. Similarly here, these 2 trailing zeros are significant. We are saying we know that that's a 0, just like I drew that meniscus that hits 0. And I'm saying, hey, I measured that and it's 0, or it might be 1, or it might be, the one below it, 0.99. But we know it to be a 0 in those 2 places. Okay. So here, these 2 problems, and the author has deliberately done this so that they're testing all of the different possibilities. So they're testing leading zeros and trailing zeros, and trailing zeros when you have scientific notation, and captive zeros with scientific notation. So again, I'll just appeal to my own experience as a textbook author and having to write problems. You write problems to try to illustrate important points and to get the whole scheme, the whole gambit of different problems that people are going to run into. They don't really care that there's 5 sig figs here. What they care about is that you know the rule for counting sig figs so that you can do any problem that you come across. So in every problem that you do, you might want to ask yourself, what is the author trying to teach me in doing this problem? What am I supposed to learn from it? That's a great way to work through problems, because then you can apply that information and those ideas on the exams. You're not just memorizing an answer for one particular kind of problem, you're learning about problem solving. So that's the whole point of this video. Stick to it. Keep coming back to the text, keep coming back to problems. Don't immediately go to somebody and say, well, how do you do this? Explain it to me. You will learn it a lot more richly if you really grind through and try it. I'm not suppressing questions. Questions are great, but if you've done some work, then the questions that you ask are a lot more targeted and you'll learn a lot more. So be reading that textbook. It's your friend. It's packed full of good information that's going to help you do well on exams. I hope this helps. So one giant recap here, read a small section. Don't read the whole chapter. Do some problems on that section, test yourself. If you didn't get those problems right, go back. You know where that material is. It's only in the last 1 or 2 pages. You don't have to flip through the whole chapter. So you're doing yourself a very efficient favor. And then if you get those problems right, go on to the next section. So now that we've done that section and hopefully you've got these things right, go on to the next section and read that section about manipulating problems, doing multiplication, subtraction, division. The next video is going to be about the worked out problems, the examples that come in the next couple pages. Okay, so see how you can learn on your own to do problems that have significant figures where you're adding and subtracting and multiplying and dividing different numbers of sig figs and learning the rules for that. And that'll be the next video. Thank you.